Yeah, so let's review a bit. So you see, this is a sequence, or this is a permutation of 7, meaning it is an reorder of 1 to 7, right? In some order. And if we keep the order and pick some numbers, right, like a 1, 3, 7, it is called a subsequence. But like a 1, 7, 3 is not a subsequence because it's not consistent with the original order. Yeah. And by increasing subsequence, it means it is both a subsequence and also it is increasing. So meaning each number next, each following number is greater. And we have seen why. So this is a definition. And the first, so each of this is a pair, right? And the first number in the pair is meaning the length of the longest increasing subsequence, ending with 3, right? For 3, an increasing subsequence can be 1, 3, so the length is 2. And a decreasing subsequence can be 4, 3, right? I mean, it cannot be 4, 3, 2 because we want it to end with 3 here. So it's 2. Okay, let's review a bit. So I want each of you to also explain why is like maybe for 7, why is it 3 and why is it 1? Yeah, maybe Hector, can you explain playing this pair for the 7? For the subsequent and with 7. Yeah.
Uh, so the increasing subsequence will be like 3, 7, 4, 7, and 1, 7, which is 3, and then
But
the
3, 7 is only 2, right? 3, 7 is 2. So the length of 3, 7 is 2.
yeah, yeah. I mean the longest length of the increasing subsequence is 3 because it's 137 or
Yeah, 1,
either
3, 7.
147.
Yeah, 1, 4, 7. Yeah,
And the
both 1, 3, 7.
decreasing
Yeah.
yeah, yeah. And for
Okay, why is this
decreasing
one? Yeah.
subsequence it's only 7,
Yeah.
so the length is 1.
Yeah, exactly. Because if it's decreasing, 7 is already the largest number here. So in order for it to be decreasing, you cannot be 3, 7 because 3, 7 is increasing. So 7 itself, right? Only one number itself is of course decreasing because it has nothing else to compare with. So it is both increasing or decreasing. So the length of the longest decreasing subsequence is 1. Yeah. And maybe Emma Shi, can you help us answer this? Like why is the 2, 2, 3?
Uh,
Yeah. So anyway, 2, right? Oh,
yeah,
by the way, are you here in the previous lecture?
yeah.
Okay, okay.
Um,
Yeah. They can help us answer this. Yeah. So analyst 2. Like first, let's find the an increasing subsequence analyst 2. So what can that
uh,
an increasing subsequence?
1, 2.
Yeah, 1, 2. Yeah, that is the longest one, right? Because 2 is already small enough. And the only thing smaller than 2 is 1. So 1, 2 is the longest subsequence that is increasing, and then that is also and with 2, right? So 1, 2, 1, 2 is the longest one, and its length is 2, right? So this is 2. And can you find the decreasing subsequence?
Uh, 4, 3,
Yeah,
2.
4, 3, 2 is a decreasing subsequence. Yeah, that's very correct. And it's the longest one. Because if it's 7, 2, then its length is 2, right? 4, 3, 2 has a length of 3. So that is why this is 3. Okay, cool. That's very correct. And maybe Phoebe, can you answer like the case when it ends with 6?
Um,
So what is an increasing subsequence and with 6?
increasing.
Yeah, increasing.
6, 7.
Yeah, I mean, for it to be a subsequence, you cannot go backward, right? I mean, subsequence meaning you can jump, like you can like 1, 3, 2. This is a subsequence. You can jump, but you can never say 1, 2, and you go backward to 3. So now you understand what a subsequence can be. Right? I mean, 1, 4, 3 is also a subsequence. So subsequence meaning you can keep some numbers and throw away some numbers, but you need to keep the order, right? So 1, 4, 3 is a subsequence, but it's not.
Oh.
Yeah. So what's an increasing subsequence ending with 6? By ending with 6, meaning you cannot start from 6, right? So you end with 6.
1, 4, 3, 6.
1, 4, 6. Yeah, that's very correct, right? So 1, 4, 6 is a subsequence because you see you jump these three numbers, right? You jump and you keep the original order. So 1, 4, 6 is a subsequence and it's also increasing because of 4 is greater than 1, 6 is greater than 4. Yeah. So
Oh.
the length is 3, right? The length is 3. And you cannot be longer, right? 1, 4, 6 is the longest one. I mean, you can also be 1, 3, 6 or 1, 2, 6, but the length is also 3, right? It's not longer. So we write 3 here. Can you give us another like decreasing subsequence and that end with 6?
7, 7, 6.
Yeah, that's very correct, right? Because 6 is already large enough, and the only number larger than 6 is 7, right? So it can only be 7, 6. And fortunately, 7 comes before 6, right? So we can have 7, 6 as a subsequence. I mean, if seven appears later than 6, then we cannot have 7, 6 because we need to keep the original order, right? The original order of this permutation. Yeah. So 7, 6 is a decreasing subsequence, and it's already the longest one because 7 is the only number larger than 6. So it cannot be longer. So 2 here. Yeah. So the length is 2. Cool. That's really great. And Emma Yu, can you help us answer the 5 here?
Like an increasing and a decreasing subsequence.
Yeah, yeah. So why is it?
Uh, uh,
So
what's the question?
the question is that why is it 3 here and why is it 3 here, right? Explain
Uh,
this. Yeah. I mean, you can explain step by step, right? First, you need to find a increasing subsequence, and you argue that it is the longest one. Yeah.
uh, an increasing is 1, 3, 5.
Yeah, 1, 3, 5, correct. And you cannot find a longer one, right? So 1, 3, 5 is the longest, right? It can be
Uh-huh.
1, 4, 5, 1, 2, 5, 1, 3, 5, right? But the
Mm-hmm.
length is 3. So it is 3 here, right? Okay. So why is
Oh,
3 here? Yeah, yeah.
because decreasing is 7, 6, 5, so it's also 3.
Yeah. And of course, it's the longest one, right? Because there are only two numbers larger than 5, and you already use them all, right? So 765 is, of course, the longest one. So we write as 3 here. So now you all understand why. So what does this pair mean, right? So for each number, it has a pair. So the first number is the longest subsequence that is increasing and that ends with 7 and with this number, right? And the second number is the length of a decreasing subsequence. So that means a subsequence that is decreasing, that ends with this number, right? So each number has a pair. Okay. So then our claim is that all these ordered pairs are distinct. So meaning that, say, the longest increasing subsequence, right? So for the longest subsequence end with 7 and the longest subsequence end with 2, they cannot have like both the same length. So we cannot have like okay the length of the increasing subsequence end with 7 equal to the length of increasing subsequence end with 2, and also the length of decreasing subsequence end with 7 also equals to the length of decreasing subsequence that end with 2. So this can never happen. You see, neither of these two pairs are equal. So maybe the first number is equal, right? 3 equals to 3, but the second number is not. And we now need to prove that this will always be true. So I mean this is what we get from one specific permutation. So we want to claim that no matter what the permutation is, this is always true. So then why? Maybe Jason, can you help us read the first two paragraphs? Yeah, we can read
Fir-
slow. Yeah.
Okay, first we use the pigeonhole principle to show how this claim implies our theorem, and then we will prove this claim. The pigeons will be the number 1, 2 to n of the permutation, and the holes will be the ordered pairs. Let L1 be the length of the longest increasing subsequence of our permutation, and LD be the length of the longest decreasing subsequence. It is clear that all the ordered pairs are less than or equal to L1, comma LD, so the number of pairs is at most L1 times LD.
Yeah. Okay. So this is uh, something that we need to understand. So first, so the lecture note, right? The lecture note is written like in backward order. So we first assume this claim is correct, and remember our ultimate goal, right? Our ultimate goal is to prove this theorem. This theorem says if we have a permutation of n, meaning like 1, 2, 3, 4, dot, dot, dot until n, and we shuffle it, we randomly reorder it into some order, then it is guaranteed to have either an increasing subsequence or a decreasing subsequence that is pretty long, that is longer than root n, right? So this is what we want to prove ultimately. And so the lecture notes said, so instead of proving the claim directly, we first assume this claim is true, and we use this claim to prove the theorem here. So how do we use a claim? First, since we have a permutation from 1 to n, right? So it's a reorder of 1 to n. And do you remember how many permutations are there from 1 to n? I mean, this is unrelated, but it's a review. Maybe like I'm not sure. Do you remember how many permutations are there from 1 to n?
I forgot the expression.
The expression, but can you do you know how to? So you do not need to memorize the expression, but can you like start working out the solution? Like say
Like
yeah.
n times n minus 1 times like until you times 1.
Yeah, exactly. So that's the exact answer. Yeah. So because for the first choice, you can be either 1 or 2 or 3 until n, right? And for the second choice, since you already for the second position, since the first position you already used up one numbers, so you have a n minus 1 remaining, right? So n times n minus 1 times n minus 2 times dot 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 times to 1. This has a mathematical name. It is called n factorial. Yeah. So let me open a new window. Yeah, so it's called n factorial. It's like this. So n factorial. Let me send this actually to your group. Equals n times n minus 1 times dot 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 times 1. Yeah. So this is an expression. So it's n factorial. Yeah. Okay. Oh, and also let me write the English word. So this is called n factorial. Yeah. Okay, so the holes will be the ordered pairs. So meaning like how many ordered pairs are there for this specific permutations? Yeah. So the pigeons will be the numbers of the permutation, and the holes will be the ordered pairs. So let Li be the length of the let me see what is so what it is trying to get. So Li be the length of the longest increasing. So you see we have a bunch of pair, right? A bunch of pairs here, right? And Li be the length of the longest increasing subsequence of our permutation. So if Li is the longest increasing subsequence, so then what do we know about the first number here? This is deep question. Maybe like Jason, do you know? So say Li is the length of the longest increasing subsequence of the whole permutation. So whole permutation means 1, 4, 3, 7, 2, 6, 5. The longest, the longest, the length of the longest increasing subsequence is Li. Then what do we know about the first number of the pair here? Can you give a guess or give a reason, give a thought?
The first number of the pair, the largest first number of the pair is Li,
Very
I
good.
guess.
Yeah, that's very good. And we can also say in this case, all the first number is smaller or equal to Li, right? So it is bounded, right? So whenever we want to use pigeonhole principle, we want to count the number, right? And we want the number to be bounded by something. Say we say that the hole, right? The number of holes is less than maybe 10, and the pigeons is greater than 15, right? Then 15 pigeons fly into 10 holes, right? Fly into holes that is less than 10. Then of course two pigeons will fly into the same hole, right? So we want to bound the number of holes, and we want to upper bound, right? We want to say the holes is not the number of holes is smaller than something, and the number of pigeons are greater than something, and then we found okay, then the number of pigeons is greater than the number of holes, and we can use pigeonhole principle, right? So that's what pigeonhole principle is all about. So we already know that the longest increasing subsequence is Li, and this is the length of some increasing subsequence, right? Specifically, this is length of the increasing subsequence that ends with 1, right? But Li is the length of the longest increasing subsequence in the whole permutation. So we don't constrain it to be either end with y1 or end with 4, end with 3. It can end with anything. So this will be of course larger than any of this number, right? Right, larger or equal to any of these numbers. So the first number of the pair must be smaller or equal to Li. And similarly, LD is the length of the longest decreasing subsequence inside the whole permutation, right? So since this is the length of the decreasing subsequence end with 1, this is the length of decreasing subsequence end with 4, right? And the LD is the length of the longest decreasing subsequence that can end with anything. So of course, all the second number, right? All the second number in the pair must be less or equal to LD, right? But we also know that the number, right? Either the first number or the second number. So they must be greater or equal to 1, right? Because because like a 3 itself is a subsequence and it has length 1. So the length must be greater or equal to 1. Okay, so then we know that for any pair, right? For any pair here, for any pair here, the first number is in the range from 1 to Li, and the second number is in the range from 1 to LD, right? So, but if we assume that all order pairs are distinct, right? So to prove this theorem, we first assume this claim is correct. So later we'll prove this claim. So if we assume this claim is correct, then all pairs are different, right? All pairs are different, and their range is so all the numbers, right? If for all the like first number is between 1 and Li, and the second number is between 1 and LD. So can anyone answer like why the number of pairs is at most Li times LD? So the number of pairs. Maybe Amayu, do you know how to answer this? Do you know why? Why is this? So the number of pairs is at most Li times LD.
I'm still thinking. I'm not really sure.
Yeah, let's think step by step. So like can you tell me like what are possible so what is the maximum number of your choices for the first number of the pair? So the pair has two numbers, right? So what is like a maximum choice for the first number? Emma, you can still answer this.
Uh, uh,
So what is the range what is the range of the first number?
like, mm,
The range is 1 to Li, right?
yeah.
because it must be greater or equal to 1 and less or equal to Li. And
Uh-huh.
what is the range for the second number?
1 to LD.
So how many different numbers can we have? Like how many
Uh,
different pairs can we have?
Li times LD.
Yeah, exactly. So you understand this, right?
Mm-hmm.
And yeah, I still need you to answer the questions. So then you need to think. So I mean, since we have Li traces for the first number and LD traces for the second number, and of course different pairs, number of different pairs is Li times LD. But why is our number of pairs at most Li times LD? I mean, because it is because we assume that all order pairs are distinct, right? So
Mm-hmm.
in our case, like each number the pair each number corresponds to is different. So that is why we can have at most this number of pairs. Okay,
Mm-hmm.
yeah. So you see, you can understand this. Okay, so let me actually read the following part. Okay, so if we assume the claim that each pigeon fits into a different hole, right? Then we have that the number of pigeon is at most the number of holes. There are n pigeons and Li times LD holes. Yeah. So actually, let's forget about pigeons and holes. So it is just simple. So we don't need to explicitly use pigeonhole principle at all. So let me explain. So say we have n numbers, right? Since this is a permutation of n, right? So can n be very large? N cannot be very large because if n is like 100 or n is very large, even if n is larger than Li times Ld, what will happen? Because each number, right? Each number here corresponds to a pair, right? So if n is larger than Li times Ld, then we have we have a lot of pairs, and some pair by pigeonhole principle, right? So say n is larger than Li times Ld, since we only have Li times Ld different number of pairs, and if n is larger than it, then two numbers, right? Then two pairs corresponding to two numbers must fit with the same pair, and that contradicts with our claim that all order pair here are different. So do you get this? Maybe like Phoebe, can you also explain again why n cannot be too large?
I still don't know.
Let me continue to explain. So you see, each number corresponds to a pair, right? Do you agree with this? Yeah. So if we have n numbers, then we have n pairs, right?
Yeah.
And we just said so for each pair, the first number is between 1 and Li, and the second number is between 1 and Ld, right? So in this case, we can only have Li times Ld different pairs, right?
Yeah.
Yeah. So what will happen if n is very large?
Um.
You can think of let's give a concrete number. So say Li times Ld equals 5, right? So what if n is 7? Then we have seven pairs, right? So if n is 7, then each number corresponds to a pair. So we have seven pairs, right?
Yeah.
And what is Li times Ld? Li times Ld is the number of different pairs we can have, right? Because in order for the pairs to be different, we only have Li different traces for first number and Ld different traces for the second number, right? So we only have five different number of pairs, but you have seven pairs. Then of course two pairs must be the same, right? Meaning like two pairs must have the same first number and same second number. Do you get this?
Maybe.
Can you explain in your own words? I'm not sure if you even get why is so what does Li times Ld mean here? Can you explain what Li times Ld is expressing?
Number of the pair.
What pair? So Li times Ld. So what does that express?
Um.
I mean, you can think of it this way, right? So the first number cannot be greater than Li, right? And the first number must be an integer because it is a length. Do you agree on this?
Yeah.
Yeah, so the first number can only be 1, 2, 3, 4, dot 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 to Li, right? And the same applies to the second number. The second number is also an integer, and it is also between 1 and LD. So the second number can also only be like 1, 2, 3, 4, dot 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 LD, right? And what's the number of different combinations? So the first number can be 1 to Li, the second number can be 1 to LD. So if you count like how many different pairs are there, it can only be Li times LD, right? Say first number, right? See this concrete example. First number, if it can only be 1, 2, 3, and second number can only be 1, 2. Then how many different pairs are there? It's 3 times 2, right? Because it can be either 1, 1 or like a 2, 1, right? So 3 choices for the first number and 2 choices for the second number, right? So okay, 1, 2 and 2, 2 and 3, 2. So there are like a 6 number of different pairs. Do you get this?
Yes.
Yeah. So what if you have 7 numbers, right? What if you have like a permutation? So what if n equals to 7? So if n equals to 7, what happens? You have 7 pairs, right? But you only have 6 different values for pairs. Then of course 2 pairs must have the same value, right? To get this.
Yes.
Yeah, so n cannot be too large, right? Specifically, n must be smaller or equal to Li times LD, right? Because Li times LD is a number of different pairs, right? And we know that for each n, right? For each number here, it must correspond to a pair that's distinct, right? So each number corresponds to a pair, and no two numbers can have the same pair, right? So n cannot be too large, right? Specifically, we only have Li times LD number of different pairs. So n cannot exceed this, right? If n is greater than this, by pigeonhole principle, then you must have two number, right? Maybe like 4 and 7. They correspond to the same pair, right? So they are both 2, 1 and 2, 1. Do you get this?
Yeah.
Yeah. Okay, cool. So now by pigeonhole principle, so I think now everyone are able to understand this. I mean, it is hard. It is like natural if you find it hard to understand it in the first pass, right? I send you the lecture notes and you can read it again because this is like pretty deep my thought. Though it did not use any like any really like fancy mathematic symbols or like mathematic concepts, but it is still hard. You see, this lecture, so you should be proud of yourself. This lecture actually comes from MIT, so it is a college level math courses, and it's taught by MIT. You see, it's from math.mit.edu, right? This is like a MIT level of college mathematics. So the reason I select this is that it did not use any like calculus or it did not use any like linear algebra. It did not use any specific college knowledge. It's all like a middle school knowledge. It is all middle school knowledge, but it is a trick and it is convoluted in terms of thought. So this can practice your like a thinking process. Yeah. Okay. So now we know that Li is smaller or equal to Li times LD. So in order for this to be true, then either Li is greater than root n or LD is greater than root n. Can someone explain this? Maybe Emma Shi, can you explain this? So why is n smaller than this? Then we must have this.
Uh, because
I can give you a hint. You can use proof by contradiction. Do you know proof by contradiction?
no.
So in order to prove that this is true, you can try to think, what if this is not true? So what happens if this is not true? Can you translate the reverse of this? So either Li is greater or equal to this, or LD is greater than or equal to this. So what is the reverse of this?
L1 is smaller than
Root 10.
this and yeah, and LD is smaller than
Perfect.
this.
Perfect. So that is the reverse, right? So if this is not true, then Li is smaller than root 10, and LD is smaller than root 10. And what will happen? So Li is smaller than root 10, and LD is smaller than root 10.
Like if we times like these two together, then
Yeah.
maybe L1 times LD, it could not be bigger or equal to n, so
Exactly. So if we time them together, since this is smaller than root 10 and LD is also smaller than root 10, their multiplication must smaller than root 10 times root 10, which is n, right? So then you get n is smaller than n, which is of course wrong, right? Yeah. I think you get the idea, right? So this tiny step is called proof by contradiction. So if you want to prove something and you don't know how to prove, you can assume it is wrong, and then you find okay, it cannot be wrong, so it must be correct, right? So if something cannot be wrong, then it must be correct, right? So you assume this is not true, and then you find Li is smaller than root 10 and LD is smaller than root 10, and then that will get Li times LD is smaller than n, right? Smaller than root n times root n, which equals to n. Okay, yeah. So after you assume this is not true and you get Li times Ld is smaller than n, and you see, oh, Li times Ld, we already say it must be greater or equal to n. It cannot be smaller. It cannot be both greater or equal to n and smaller than n at the same time, right? So that makes a contradiction. So it means this statement must be true. So does anyone still remember what is this? What is Li and what is Ld? Maybe Jason, can you explain like what can we get after we found Li is greater or equal to root 10 and or Ld is greater or equal to root 10? So what is Li?
Uh,
What is Ld?
Li is the longest increasing subsequence ending with I. Oh wait, what? I'm
Yeah.
not sure if it. Uh,
So what do we
it's the
have?
longest increasing subsequence in the entire permutation. Yeah, I was wrong. So and then LD is the longest decreasing one, so that we basically prove the thing that we were trying to prove in the start.
Yeah, very
Using
good. Very good. Yes, so basically we just prove that the length of the longest increasing subsequence or the length of the longest decreasing subsequence must be greater or equal to root n. But yeah, Jason, can you can you like go like one step further? So why does this greater or equal to root n means it is greater or equal to the ceiling of root n? So why can you round it up?
Because they are integers, I guess.
Yeah, very good. See, an integer is greater or equal to 3.2, right? So it cannot be 3, right? So you cannot round down. 3 is not greater or equal to 3.2. So since Li is an integer, you can only round up, right? This is the beauty of the discrete math. This is called discrete math. I mean, normally, if you are greater or equal to something, then probably that's the strict boundary. You cannot like greater or equal to something even higher, right? You see, the ceiling of root n is usually greater than root n, right? So it's some like a larger number, and you can even like make it larger. It is because Li is integer, right? So like if an integer is greater or equal to 3.2, then that integer must be greater or equal to 4. So that is very beautiful, right? You can even run this to an even higher result, a more stronger result. Yeah. So in this sense, we just prove if all these ordered pair are distinct, right? Then the theorem is true. The permutation of n has an increasing subsequence or a decreasing subsequence of less at least the ceiling of root n, right? So let's summarize again how we prove this, right? So first we assume Li, right? Li be the length of the longest increasing subsequence, and Ld be the longest length of the longest decreasing subsequence of the permutation. And then we found that the pair, right, the first number of the pairs must be in the range of 1 to Li, and the range of the second number of the pair must be in the range from 1 to Ld. So how many different pairs can we have, right? How many different pairs can we have? We can have at most Li times Ld different pairs, right? And if the claim is true, meaning that each number, right, each number corresponds the pairs each number corresponds to must be different. Then we cannot have too many numbers, right? Because if our number say n is greater than this value, then by pigeonhole principle, then it must exist two numbers. They correspond to the same pair, which makes this claim not true, right? So we are assuming this claim is true and trying to prove the theorem here. So then n must be not greater than Li times Ld. So n must be smaller or equal to Li times Ld. And that means that either Li is greater or equal to root n, or Ld is greater or equal to root n. And the reason is that if neither is greater or equal to root n, means that both of them are smaller than root n, then their product must be smaller than n, and it cannot be greater or equal to n, right? So this must be true. And since Li and Ld are integers, so if they are greater or equal to root n, they are naturally greater or equal to the theory of root n. So that's how we use pigeonhole principle and this claim to prove the theorem here. And this theorem is actually quite interesting. It's like you shuffle like a 1 to n, right? You shuffle them randomly. You reorder them randomly. Then you can always skip some numbers and get a quite a long increase in subsequence, right? So even if you you can deliberately make it like a very messy and deliberately try to make every number like in a decreasing order. So you see, this is what we call the art of balance, right? So it means that no matter how you shuffle, no matter how you reorder, you must either have a very long increase in subsequence, or you must have a very long decrease in subsequence. So say if you make the permutation something like this, 7, 6, 5, 4, 3, 2, 1, right? So then the longest of increase in subsequence is just 1, right? Because it can also only be 7. You have 7 cannot increase, 6 cannot increase because 7 happens before it, right? So if you are making the length of the longest increase in subsequence very small, then you have a very long decrease in subsequence, right? So it means no matter how you reorder them, right? You can reorder them to make it really hard to find the long increase in subsequence. But at the same time, you are increasing the length of a decreasing subsequence, right? So so no matter how you order the order 1 to n, how you make a permutation, you cannot both decrease the length of an increasing subsequence or the length of and so you cannot decrease the length of an increasing subsequence and the length of a decreasing subsequence, right? So there must exist either an increasing subsequence or a decreasing subsequence with a pretty long length, right? So this is called the art of balance. Yeah. So now we only have one thing to do. So we already used this claim for free to prove the theorem. Now we need to prove the claim, right? So to prove the claim, so remember the claim is that this claim we have already shown in the previous lecture. So each number, right? Each number has a pair, and then the first number of the pair is length of the longest increasing subsequence ending with this number, right? And the second number corresponding to the length of the longest decreasing subsequence ending with also ending with this number. Okay. So suppose that we have two numbers in our permutations, s and t, with s coming before t, right? So it is still like trying to maybe prove by contradiction or something like that. So suppose we have two numbers, right? We want to and say s comes before t and s has a pair ab, right? Meaning a is the length of an increasing subsequence ending with s, right? B is the length of a decreasing subsequence ending with s, right? So say s is a number before t. They are both number between 1 and n, right? Because they are among like a permutation of n. And AB is a pair corresponding to s, and CD is a pair corresponding to t. And what will happen? So there is an increasing sequence of length A ends with S, right? So meaning so A means that there's an increasing subsequence that end with S. And there are two cases. So case one is S is smaller than T, right? So if S is smaller than T, what do we get? So what do we get for C? Maybe Hector, can you answer that? So say S is less than T. So what can we say about C? What can we say about the C? The number C here.
So S is bigger
Smaller
than
than
T
T.
or less?
Smaller than T.
So
So
S is smaller than T, then C is A plus 1.
I mean,
Or
C is not necessarily A plus 1. It can be A plus 2, A plus 3, right? Because they are a bunch of numbers.
bigger than A.
Yeah, so C must be bigger than A. So, I mean, that already prove our claim, right? Our claim is that AB and CD cannot be equal, right? So if C is already greater than A, then of course they are not equal, right? So you see, the claim is actually pretty easy to prove. So for two numbers, S and T, since they are permutation between 1 and n, so S and T cannot be equal, right? Because you shuffle 1 to n, like each number 1, 2, 3, 4, 5, dot, 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 n. They are different numbers, right? If you shuffle them, you can never get two numbers at you can never get to the same number at two different positions, right? Because each number appear only one. Okay, so you can either be s smaller than t, and you already get an increase in subsequence and with s, and you can just append, right? You can just put t at the end of the subsequence. So then you get an increase in subsequence that has length a plus one, right? So c must be at least a plus one. So c is greater than a, right? So similarly, what will happen if s is greater than t? Emma Shi, can you answer this? So we already know what will happen if s is smaller than t. What if s is greater than t?
It will be the opposite.
Yeah, can you explain it in full, explain the full logic? So what will happen? So between A and C or B or D, B and D. So what,
Uh,
remember that S is like greater than T. What will happen?
um, A and C are like the
I mean, so A and C you don't know, right? Because A is an increasing subsequence, right? C is also the length of an increasing subsequence, but the S is greater than T, so T cannot be append to an increasing subsequence, right? So maybe let's try B and D. Do you find any relation between B and D?
B and D are both decreasing substance, so maybe like
Yeah,
B will be
let
bigger
me
than
give you a
D.
hint, right? So B is already a subsequence and with S, right? So B is already the length of a subsequence and with S. Do you get this?
Yeah, yeah.
So what if we append T to that subsequence? I mean, add T to the back of.
Oh, then then B should be bigger than D.
Yeah, so D should be greater than B, right? Because the subsequence end with T, since T is smaller than S, you can append T to the end of a decreasing subsequence and it gets longer, right? So of course D must be greater than B because end with T should be longer than end with S. Do you get this?
Okay.
Yeah. Do you really get this? Like if S is greater than T?
Yeah.
Okay, cool. So then we found that A, B, and CT can also be not the same. Could also not be the same, right? So so like if S is smaller than T, then C is greater than A. If S is greater than T, then B is smaller than D, right? So either A is smaller than C or B is smaller than D for any two different numbers. So it means that these two pairs can never be the same, right? So it seems that this like claim is easily proved. Yeah. By the way, so this theorem itself, right? This is so you should be proud of yourself if you now totally understand this theorem. I mean like some of you may understand every step, but if you still work on yourself, you cannot get the whole proof. But I really believe like some of you can already get the whole proof independently after this lecture, and you should be really proud of yourself. So for one thing, this is MIT. This is like college level math and from the most famous mathematical from the most famous technology institution, right? And also, I don't know if you know this is also a very old International Math Olympiad. I don't know if any of you have heard IMO. So it is the hardest mathematical Olympiad, hardest mathematical contest that ever exists in the world. So so if you get an IMO gold medal, it means that you are the best student in math among your age, and you are guaranteed a position in MIT or Princeton or maybe not Yale. Yale is not interested in math, but for MIT and from MIT and Princeton specifically, if you are a IMO gold medal, you don't even need anything else. You can get admit straight into the college. But it is hard. It is hard because there's like less than 10 gold medals every year. Yeah. So and this problem itself is an IMO problem. So IMO actually only have six problem. So if you get this problem, you get like 1/6, 1/6 per 1/6 like a fraction of the full score. Yeah. And normally for an IMO contest, if you get maybe 3 to 4 problems out of 6 problems, you can get an gold medal already. Yeah. Okay. So that means so you see the proof is actually not very long, right? So the proof is from here to until here. It's not even it's not it's merely one page. Yeah, but the thought process is quite like deep. And you see this is very subtle, right? So who can think of a way to actually create a pair for each number, right? This is very hard to come up with. Okay, so maybe let's show that our theorem. So find permutations of n that has no increasing or decreasing. Okay, so this will be an exercise. So let's create. So let's actually create. So it is asking us to find a permutation. So create a permutation that has no increasing or decreasing subsequence longer than root n theory. So for example, in the case of 1, 2, 3, 4, 5, 6, 7, right? In the case of this, it means so then the ceiling of root 7. Can someone answer this? Maybe Mark? Do you know what is the ceiling of root 7?
Um, 2.93.
Yeah. So you don't actually care 2 point what it is, right? As long as it's 2 point something, then the ceiling is 3. Yeah. Okay. So now let's shuffle this, right? I will give you 10 minutes. So this will be treated as either both a break and time for you to exercise. Try to get try to get a pencil and a piece of paper and try to reorder 1 to 7. And in your permutation, right? You should get a permutation like 3 to, for example, 3 to 1, 4, 5, 6, 7, right? So in your permutation, you should not have an increasing sequence, right? Increasing subsequence with length 4, right? Could not have an increasing or decreasing subsequence of length 4. For example, this permutation failed because it has an increasing subsequence 4, 5, 6, 7. Actually, it has an increasing subsequence 1, 4, 5, 6, 7. The length is 5, right? So it's not correct. So try to get a permutation. I mean, there are tons of permutation out there, right? There are 7 times 6 times 5 times 4 times 3 times 2 times 1. This number is greater than 1,000. So you have yeah, this number is actually not greater than 1,000. This is oh okay. Actually, so 4 times 3 times 2 times 1 is 25 times 5 is 120 times 6 is 720 times 7 is 5040. So it's a 5040. Yeah. So you have like more than 5,000 permutations out there, and try to find one permutation that doesn't have a increasing subsequence of length 4, and it also doesn't have a decreasing subsequence of length 4. Yeah, I'll give you 10 minutes to do this exercise. And if you do it really quick, you can take a break. Yeah. Okay, let's get back. So let's see if you come up with some permutation. Maybe Mark.
Okay, so I thought of 4, 6, 1, 2, 5, 7, 3.
Okay, so let's see. What could be a increasing subsequence here, like 1 to 5, 1 to 7, 1 to 3? So all like a line three, right? What is a decreasing subsequence? Maybe 6, 5, 3, 6. Yeah, I think this is a good example. And yeah, the length of the decreasing is also three. The longest decreasing subsequence is also three, right? 6, 5, 3. Cool. Very cool. So I'm not sure. Do you have another example?
I can't really see oh, now I see the screen.
Yeah, I mean, do you have an example of a permutation that have an increasing or decreasing subsequence of lines four? So Mark just gave a very good example here. Do you have another permutation?
No, I think I have to think of another one.
Oh, you haven't think of another one, right?
Yeah.
Okay, cool. Maybe Jason, do you have another example?
2, 1, 4, 3, 6, 5, 7.
2, 1, 4, 3, 5, 6, 7.
6, 5, 7. 6, 5,
Six,
7.
five, seven. Okay. 2, 1, 4, 3, 6, 5, 7. Okay. So increase.
Wait,
Uh.
uh,
Oh, oh,
never,
so
wait, I think it's wrong. Wait, never mind. Let me
yeah.
think.
Yeah. So because we have 1, 3, 5, 7, right? So it's last four. Yeah.
Okay, never mind. I might be stupid. I didn't notice
I
that.
mean, you can rework on that after the lecture. This will be like both Amash and Jason. You can working like this. You can working on the permutation, right? Try to write some random permutation and see if they have a decreasing or increasing subsequence of length four, right? So this is a very good example. So yeah, this one is a good example. Okay, let me throw away the this and let's only keep the example, the working example here. Okay, so maybe Emma, do you have another permutation?
Maybe 6, 2, 4, 7, 1, 3, 5.
Okay, so increasing subsequence 2, 4, 7, right? 2, 4, 5. Yeah, the increasing is at most three. Yeah, so maybe decreasing 6, 4, 1, 6, 4, 5, 7, 7, 1, 7, 5. Yeah, this is a very good example. Yeah, this is another example where it doesn't have an increasing or decreasing subsequence of last four. Phoebe, do you have another example?
5, 3, 7, 1, 6, 2, 4.
5, 3, 7, 1, and then what?
6, 2, 4.
6, 2, 4. Okay. So for increasing one, 1, 2, 4, right? Three, yeah, 3, 6. So increasing is at most three, and for decreasing one, 5, 3, 1, 7, 6, 4. Yeah, this is also a very good example. So we have three example already. Yeah. Okay. So very good. So most of you have completed this exercise correctly. So this exercise shows that this theorem is already the strongest one, right? It cannot be stronger. So we cannot say, oh, we have either an increasing subsequence or a decreasing subsequence of length like even greater than the ceiling of root 10. That's not even possible because we already gave an example that both the longest subsequence and the and the length of decreasing subsequence like does not exceed the ceiling of root 10. Yeah, you cannot be even larger. So that theorem is the strongest that we can get. Okay, now let's work on this example. So maybe Mark, can you help us read the first paragraph?
20-player game. Now to another application. Consider the game with 20 questions. Here, one player thinks of an object, and the second player asks yes or no questions until she guesses it. We'll ask for the largest number of distinct objects that can be identified in such a game. One thing to recognize is that the strategy is adaptive. The cave question may depend on the previous cave minus 1 question. Consider a strategy of a guessing player. On her first question, she may ask the traditional question, is it bigger than a bread box? If the answer is yes, it will be reasonable to continue. Is it smaller than an elephant? While if the first number is no, she will want to give a different question. However, we restrict her to follow a deterministic strategy. If she gets a yes answer to the first question, we assume that she always asks the same second question.
Okay. Amash, can you read the second paragraph?
Even though the second question may depend on the answer to the first, if our player is to identify an object from our set of objects definitively, then there cannot be two objects in our set which give the same answers to all the questions. If there were, then the questions would have to be the same for each of these two objects, since the questions may depend only on the previous answers. Thus, when the guesser got to the end of her 20 questions, she would not be able to determine which of these objects were correct or was correct. She would have to guess wrong for at least one of them.
Yeah. When the getter got to the end of her 20 questions, she would not be able to determine which of these objects were correct. Yeah. So that's for every object in our set. These objects will be like pigeons, and there must be a unique sequence of yes or no pigeonholes. There are 20 questions, so there are 20 yes or no answers, right? Each of which can have two values. The total number of possible objects is thus at most 2 to the power of 20 or a little over a million, and this bound can be achieved as there is a strategy for the guesser to distinguish the 2 to the 20 objects with 20 questions. Yeah. So basically, it talks about a strategy on how to guess, right? How to guess the answer, guess an object. So he uses 20 questions, and each question can be answered yes or no. And so um, even though the second question, so the strategy is that deterministic strategy means that you always follow a same strategy. So if she gets a yes to the first question, we assume she always asks the second questions. If even though the second question may depend on the answer to the first, if our player is to identify an object from our set of objects definitively. So this means that there are finite number of objects. So so finite numbers of possible objects. Say you think in mind of 100 objects, and you are testing one by one whether it is object number one, object number two, object number three, or object number 100. There cannot be two objects in our set which give the same answers to all the questions. If there were, then the question would have to be the same for each of these. Then the question would have to be the same for each of these two objects, since the questions may depend only on the previous answers. That's when the guesser got to the end of 20 questions, she would not be able to determine which of these objects were correct. Yeah. So this means that we follow a deterministic strategy. So whenever so I ask a question, and if you say yes, I will ask a certain questions. So no matter so it's like if the answer is yes, I will always ask the same question, and if answer is yes, I will always ask another same questions again. So I mean I have 20 questions, and each questions only depend on if the answer for my previous question is yes or no. If it is yes, I always ask a same question. If it is no, I always use another like questions prepared for the answer no. Yeah. So then if so in this way, so in this way, like if I always ask the same questions, it means that your answer for the previous question is always it's always the same, right? It's like yes, no, yes, no, yes, no. It's a sequence, yeah. And I mean, this is not a very classic example, but you get the idea. You get the idea is that the question you asked only depends on the answers to the previous questions. So in this way, if you ask all the same questions, then it means you get all the same answers for any of the questions, and that um, so that means that you have two objects that gives the same answers for all the questions you prepared. Yeah. The total number of possible objects is just at most this, or a little over 1 million. And this bound can be achieved as there is a strategy for the guesser to distinguish this number for objects with 20 questions. So it means that if your total number for possible objects is not like a grid, for example, you have a limited number of selections of may be uh, what may be a possible object that you need to guess. If the number is not greater than 2 to the 20, you are guaranteed to use this strategy to eventually find out the correct answer. So, but still, I think this is not a very good example for pigeonhole principle, and yeah, and maybe um, I think that's the end of this lecture notes. So let's skip the 20 question game here because I think it's not a very good example. Yeah. Maybe I will find some other applications of the pigeonhole principles and send as a supplement materials to you. Yeah. So let's actually go to some other stuff. Let's go over some probability. Let me see probability. Yeah. So I think most of you may have already familiar with probability, and let us not use the lecture notes. And so I don't know if you have heard of the word expected value, right? Expectation or expected value. So say for example for a coin, right? For a coin, say if I roll a tail, right? Roll a tail, we call it 0, and if we roll a head, we call it 1, right? And say the probability, it is a fair coin, right? So the probability of getting 0 is 1 over 2, and the probability of getting the 1, right, is also 1 over 2. So then what is the expected value in this case? Mark, do you know this answer? Do you know what's the expected value?
It's 0 times 1/2 plus 1 times 1/2.
Very good.
0.5.
Yeah. So expected value is just the mean value. So if for 1/2 of time you get 0 and for 1/2 of time you get 1, then the expected value is just probability times the value plus the probability times the corresponding value, or the value times its corresponding probability. So the expected value is 1/2. And say you have a die, right? A die is a more classic example. Rolling a die, you can only get 1, 2, 3, 4, 5, 6, and each number will have a 1 over 6 probability, right? So then what is expected value in this case? Put it in another word, is like what is the mean value, right? What is the mean value of all possible numbers that you can get if you roll it a lot of times, right? So what is the expected value? Maybe Amateur, do you know the answer for this question? I mean, you can. So the idea of expected value is just like you use each number times its corresponding probability, and its meaning is that
Oh,
it is the expected mean value that you get. So sometimes you roll a high number, sometimes you roll a small number, right? So the average, right? The average of all the number you roll must be approaching to the expected value. Yeah. So can you calculate the expected value in this case? So just use
One
1 times 4.
one times 1 divided by 6 plus 2 times 1 divided by 6 plus 3 times 1 divided by 6 plus 4 times 1 divided by 6 plus 5 times 1 divided by 6.
Yeah, so basically it's 1 plus 2 plus 3 plus blah, 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 plus 6, and then divide by 6, right? So it's like 21 over 6, and the value is 3.5. And that's actually expected, right? You see 3 and 4 are in the middle, right? So the expected value you get is 3.5. It's not saying that you can actually roll a die and that die shows 3.5. It's just mean if you roll the die a lot of times, and the average value you get is approximately 3.5. And this is what the expected value is all about. Okay. So now you get the idea, right? You get the idea. So it's just the value times its corresponding probability and add together. And that is the expected value. Okay, now let's actually play a game. A game that maybe a little bit harder. Yeah. So see this game. Okay, in this game, we still roll a coin. And if we roll a tail, we continue to roll. So tail, we continue to roll. And if it's a tail again, we continue to roll. And if it is a head, we stop. Right? Then how many times do we roll this die? We roll it 3 times, right? And for example, if we roll the head, and then so as long as the head show, we stop the game immediately. So the number of times we roll in this game is like 1, right? And we may be very unlucky and we roll a lot of tail and then get a head. And then how many times do we roll here? Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. So in this case, we roll 11 times before we stop the game, right? And so assume this is a fair coin. Okay. So let's calculate the probability of each cases. So maybe Jason, do you know the probability that we just roll high and stop the game?
I mean, it should be 1/2.
Yeah, it's 1/2, right? It's a fair coin, so we have a half of choice to get a tail in the first row, right? Or like half probability to get a head. So we have one half probability to roll a head and stop the game, right? Then Emma, do you know what's the probability if we roll 2 tail and then get a head? So what's the probability of these cases?
Oh, I'm not sure. Maybe 3/6. I don't know. Like, I'm really confused.
What's the probability if you just roll a tail?
1/2. Oh,
Yeah.
uh,
Then what's the
uh,
probability you roll another tail?
oh, so it's 1/2 times, no, 1/2 times 1/2 times 1/2?
Yeah, exactly. Yeah. I mean, each time either you roll a tail or a head, right? And it's just 1 or 2 probability. So time multiply them together. Yeah. I mean, if you roll it like this, right? If you roll 2 tail, head, tail, it's also 1/2 times 1/2 times 1/2. But in our game, you can't roll this because if you roll a head, you stop the game, right? So the probability that this scenario happens is also 1/2 times 1/2 times 1/2, which is one over weight. Okay. So now maybe Phoebe, do you know like what's the probability that this happens? We roll 11 times and then stop the game.
Um, could you explain the first and the second one again because I'm not sure.
I mean, the probability that you roll a head is 1/2, right? Because it's a fair coin, right?
Mm.
Okay. So what's the probability you roll a telltale head? I mean, you first need to roll a tail, right? To roll a tail, it's 1/2 probability, right?
Oh yeah.
And then you need to roll a tail again, right? Which is also 1/2 probability because in the second time, You still have one half probability to get a tail and one half to get a head, right? So to roll tail, you need 1/4, 1/4 probability, right?
Oh,
To roll
okay.
tail. And then you roll a head, which is also 1/2, right? So in total it's like 1/8 probability to get a tail head. I mean, it's also 1/8 probability to get a tail head tail, but the tail head tail can never appear in our game because whenever we see a head, we stop the game, right? Okay, so now can you answer what's the probability to get 10 tail and one head?
1 divided by 2 times 1 divided by 2 times
Yeah, exactly. So it's a 1 divided by 2
times
times
2
11 times.
11.
Yeah, you are correct. So it's 1/2 times 1/2, it times 11 times, right?
Yes.
So it's a 1/2 to the power of 11. Yeah, exactly. And to verify if we get our probability right, so we know that if we add all the cases together, we should get one, right? So every cases that could ever be happen, their probability should sum up to one, right? So what's the cases? We can either be head or tail head, or tail head, or tail head, or tail head, or tail head. Right? This is all possible ways, right? So the probability of this is 1/2 and 1/4 plus 1/8, right? Plus 1/16 plus dot. For those of you who don't know, I can give you the answer. So if you plus them all together, of course you plus infinite number of values, but you will eventually get one. Yeah. I don't know if any of you have heard about this. Maybe Jason, do you know how to prove this? Like 1/2 plus 1/4 plus 1/8 plus indefinitely, and you will get one.
I think we might be able to use the like the addition of a geometric sequence, like the sum formula for this,
Yeah.
where we can say that every time we're adding half, so it makes sense that will go to one.
Yeah, exactly. You can use the geometric sequence formula. Yeah, and to make it more simple, in the end of this lecture, I will give you another way to show it. So you can assume like t is 1/2 plus 1/4 plus 1/8, right? Plus dot. So you assume this number is t. Then what is 2t? So 2 times t, you see, it's 1/2 times 2, which is 1, right? And 1/4 times 2 is 1/2, right? 1/8 times 2 is 1/4, right? So you still plus them together. And you can observe, you see, 1/2, 1/4, 1/8. This is also 1/2, 1/4, 1/8, right? Because 1/16 multiplied 2 is 1/8, right? So this and this are the same, right? So you use the second equation and minus the first equation. What you get? On the left hand side, you get 2t minus t, right? On the right hand side, you see this and this cancel out, right? So there's only a remaining one here, right? So basically you get t equals to 1, right? See? 2t minus t equals to t, and you get t equals to 1. And maybe like you do you get this way to show why this sum up to 1?
Mm-hmm.
Okay, cool. So I understand every step, right? Yeah. And Phoebe, do you also understand this?
Yes.
Yeah. Since you say like 1/2 multiplies 2 gets 1, right? 1/4 is 1/2. And you need some observation and you find okay, this and this are the same. So 2t
Yeah.
minus t is t. Yeah.
So equal 1.
Yeah, it's 1. So this is a clever way to show why this sums until like infinite sum is 1. Yeah. So we just show. So I will leave you a homework. So I will not teach you in this lecture, but I will leave it as a homework. So we just show that this is a valid probability. So our previous way of calculating the probability is correct because all these cases you add their probability together, you get one, right? This makes sense because the probability of anything happens, right? If it's one, right? Probability one of all cases. Okay. Then what is the expected value of the length, right? Right. The number of toes. So you toss a coin, right? So what is the expected number of toes? Because in this case you toe just one time. In this case you toe two times, right? This is one, this is two, this is three, this is four, right? You may toss 5 times, or you may toss like in this case you toss 11 times until you end the game. What is the expected number of toes? Right? This is homework. What is the expected number of toes for this game, right? So just use this previous example with just the probability times the number of toes, right? So this is the probability times one. This is probability times two, right? So you can, so even if you don't know how to calculate the eventual expression, try to write that, try to write the expression. You can write down on a piece of paper and send to the group. Okay. So this is the end of today's lecture. Yeah. Thank you.